Thank you. Good morning. I'm a research scholar in the Department of Center for Product Design and Manufacturing, and Professor Monto is my supervisor. So today I'm going to talk about the assessment of information adequacy of testing products for sustainability. This is from a systems perspective and from an engineering design perspective. This is a broad outline of my presentation today. Introduction and what is the state of discourse on design for sustainability as we understand from the literature. Testing of products for sustainability, particularly as a system component formulation, as against a standalone product perspective, and the information needed for product testing when we talk about design for sustainability. And I will just summarize the arguments as part of this work and conclude with certain remarks. Essentially, the basis for sustainability, as we understand the broad term, comes from the anthropocentric formulation of the concept of sustainable development, which gathered momentum late last century. And the anthropogenic processes create entities, we call them products from an engineering perspective, that interact with the environmental processes in complex ways, and they spawn off more processes and products. From an engineering design perspective, the requirement is, if I look at sustainability as the requirement, the eternal accessibility resources for supporting human lives with an adaptive regulation of processes in the fully connected earth system. So this is what if I am a designer, system designer, this is the requirement I have in hand. There is no agreed definition of sustainability or sustainable product, as we all know. However, there is a pursuit of design for sustainability. Okay, so how does this translate into design decision making? So that is the question. So from the context of my work, the motivation is to know a priori the effect of products on the environment. Comprehensive knowledge is required, which is combinatorially explosive. We know this is going to be a huge challenge to know all these interactions, and they are bearing on the accessibility of resources. So economic and social dimensions are not in the scope of this work because I consider them as secondary and tertiary phenomena. So this inquiry dwells on the question of the prerequisites for testing product for sustainability. When can we say we can test product for sustainability? The connotation of sustainable product is analyzed from an engineering design perspective, and certain arguments are advanced for products as components from a system perspective. The methodology I follow is descriptive study from a design research perspective and theoretical. So this is broadly the agreed design, engineering design process. Okay, this is adapted from Thal and Bates, standard on engineering design. And so it primarily, like the key point here is you will see there is test in every cycle of this. Okay, so that is to make sure whatever we produce is actually doing what is intended. That's the idea of again testing, and there is a progress in terms of optimization as we do iterations of these products. So by definition, engineering design is an endeavor to change the undesirable state to a desirable state. Okay, it's also called a plan to improve, okay, by building products and services. Traditionally, desirable in engineering means improving the performance, that is efficiency, safety, cost effectiveness, so many other parameters, but only notional anticipation of the environmental sustenance. Yes, so that's the prevalent state. Products designed to promote sustainability should be testable for those requirements, whatever be the form of the environment. So from literature we see, in fact this is very common nowadays, we use improvement paradigm. So several principles of sustainability assessment for engineering are proposed. There is a study on that, and the author concludes that most of them are qualitative and generalized. So it's hard to take a particular method and apply. Sustainability as an endeavor of direction to target is criticized for the lack of clarity. This is from a system side, and because there is no target as is which is fixed. This is a moving target. And one of the definitions considers that a sustainable product is one that is more sustainable than the previous one. Again, this is an improvement paradigm. Comparison with functionally related products is proposed as a means to environmentally conscious design, the eco-design principles. A wide cross-section of literature equates sustainability to improvement of product performance. And there have been studies of the methods available already, which is standard methods available for engineering. How does it help the engineers to define sustainability milestones? Again, it relates to only qualitative aspects. And normative specifications are employed with no reference linking to the state of the larger system. This is what the missing link is. If you look at today's P4S methodologies, for example, higher energy efficiency, lower emissions, or better life cycle performance. So these are all qualitative terms, and a lot of adjectives are used to describe them. So I am taking this very simple depiction. As an engineer, how would I look at it? Okay, so there are two resources, and there are two products. Actually, one of the products is called human. The other product is a product, which is engineering products, industrial products. So one of them has a very strict requirement of, like, food is required for the population, okay, to sustain this, and the sustainability basically means the end should never go below the regeneration threshold. This is the system's perspective if I am a designer. And the second resource is sometimes called technical nutrient or technical resources. They produce technical products. They are also used as inputs for humans. Okay? Like, we can probably today live without mobile phones, okay, and clothing and so many things. So all these also go here, but they also come back to regenerate both ways. Okay? And this has to be maintained in order for this to continue. This is, as a system designer, I would take this as a starting point. So what are the parameters involved in this? I am taking a single resource, single product scenario. So in this case, the product consumes this resource at a particular rate called consumption rate, and it comes back after regeneration, and this is what a loop that has to be perpetually, it should be maintained. And there is a factor of time coming in called retention time, that is primarily due to the product living for a long time, and also recycling and things like that. So how do I design sustainability here? This is the language. Sustainability will be indicated 1 over dr. So this depletion rate should be as close to 0 as possible. Okay, ideally it should be 0, so that this is infinity. Okay, we have to live forever. That's a goal of the humankind. Okay. If it is less than 0, if it is greater than 0, then it will only persist for a finite time. So again, I am coming back to a generalized product sustainability scenario where there is a single product, single resource, and the same thing holds here. Now, how does it change from this to the product sustainability we generally talk about in the industrial engineering side? Okay, this is probably easier to understand because there is single resource. You know these parameters. You can manipulate this to get the required depletion rate, which is 0. Okay, provided we have enough information about the regeneration. This is what happens. So from this to this, now there are 10 components of that original product. So these end products have to be suitably designed so that this same criteria is met. That's what the endeavor is as far as design for sustainability of product is concerned. Okay. So I am just depicting that same thing in a simple equation. It's a generalized expression for the depletion rate that is of concern to us. So I am saying it is aggregation of multiple products, and I am splitting that product into per unit consumption and number of products, because that is very important from the engineering perspective. How many numbers will be produced of each product minus the regeneration side. So that's what. And AI is the regeneration coefficient, varies from product to product. For example, petroleum, okay, regeneration coefficient is 0. And if you take many of the natural cycles, the regeneration is close to 1. Okay? For food cycle, and it is close to 1. Okay, so it will come back again and again. And the retention time, as I told you earlier, like it's reuse and recycle, that will delay the regeneration back to the source. So I'm just taking, I'm a single product designer now, okay, from a system product designer to single product designer. What are the remaining parameters? Like I'm just rearranging the terms to make it, this is for a single product, P1, N1, T, and this one, and this is the rest. And the rest is the other terms. And so if I am designing only this, how do I know this will become 0 or close to 0 or whatever the required number is? So what is the basis for all this? So assuming the number of products to be n, that is n is very large in real terms, in actual real world, the permutations will result in many solutions meeting the basic requirements. So many options you can play with it to get that number. Normative adjustments with respect to number of products and the product consumption rates are synthesizable according to arbitrary parameters. Actually, we can do any way we want, you know, by like increasing, decreasing the combinations and then arrive at the same number. Normative criteria for sustainability should consider at least n star m specifications. There are n products and m resources, let's say. So many specifications have to be kept in mind. And in reality, n and m are large and the information need is also of that scale. Do we really have that number? I don't think so, because that is the endeavor of the science community to get this information. So it's not uncommon when component performance improvement is not in line with the system performance. This is very well documented. Rebound effect is well known effect. Euro emission after between Euro 4 and 5, actually the city emissions increase, the air quality decrease, and CO2 level crossing 400 ppm. This was recently crossed, and despite all the efforts of reducing CO2 consumption, and so it only highlights the absence of system design. Okay. So the components are being designed with certain good intention, but the system performance is not improving. At product level, designers assume the product is a need. So I am not going to elaborate because it's a philosophical and it's a normative decision again. What is a need and what is a want? Okay. But only a system designer can, if at all, decide this. But we don't have one. Okay. There is no system designer. So sustainability in several variables. This is single variable, single resource. Now, if you take several resources, several variables, there is a trend in literature that 1 or 2 indicators are used. We have seen this quite often. In fact, yesterday's presentation also we saw samples of this to represent product sustainability. So sustainability, as complex as it is a function of many variables. Selective improvement of actions would imply an OR logic. What I consider OR logic is, if we have, let's say, n variables, if 2 of them are satisfied, like the rest of the things are ignored. So it's like saying they don't matter, they don't really play a role. So this OR logic I don't think is well founded in terms of like selectively doing sustainability assessment on a couple of variables. Okay. So this is not fully substantiated. If concurrent resource requirement for each product exists, the fastest integrating resource should decide the sustainability. So the weakest link decides the strength of the chain. Right? So here also we don't, whether we know the information is what I am questioning. This is a very hypothetical description of an LC of 2 products, okay, on 7 variables. Okay. So now if you ask somebody which one is better sustainable, more sustainable, it's very hard to say. Okay. And but in this is only 2 of them. So we define indicators by aggregating this by arbitrary weightages, which we do, okay, but they are not observable in nature. Okay, these indicators are not observable, only for our convenience of depiction. If there are, let's say, million products, there are really more than million products. Okay? We need million LCS to really comprehend what is going on in the system, okay, which I don't know when that will happen. Okay? And so what is the designer's dilemma in getting to this particular aspect of design for sustainability? So the use of arbitrary references for comparison renders all realized products sustainable. Okay? So what does it mean is in a limited sense. In the sense today it is sustainable but tomorrow it may not be because somebody else has improved that already. And improvement paradigm assumes the rest of the products either remain unchanged or reducing, okay, which is very strong assumption. Okay, unless this is substantiated, it's hard to make statements like a product is sustainable. And there is no test at the product level for ascertaining this. If all the products reduce by arbitrary amounts, what is the assurance of reduction of this consumption rate or depletion rate if n changes with time? This is reality, n changes with time. The number of products are not constant. So the n of t affects convergence to system specifications. So if depletion rate is increasing and CR is to be reduced, this is a problem that we are faced with. Which product should go? Okay, no individual product designer will sacrifice their products in the, let's say, benefit of the system. So this decision is not at the product level, but it goes to the next level. And scarcity defines the definition of needs, a system level decision. Actually, in social science, this has been well studied by Ostrom and others, like institutional support for designing commons. So there, this problem is well analyzed. So what I am finally coming to is all products are components in the sustainability discourse, except when a product is a closed system. Okay, and we don't have a closed system less than the earth level system, and so we have to be really cautious when we apply the standard design principles for testing products. If the state of the system is to be known through aggregate of component performances, then an estimate of how that will be known is essential. And testing of products without system design reference does not convey any information about its contribution. Like this is like saying we have reduced CO2 emission by some amount. Okay? But what does it mean? Like, is it good? It's not good, or it's good today, may not be good tomorrow? We don't know. Coming back to the first slide which I started with. Okay. So there have been system level inquiries and thoughts on this food availability for all the population is the Malthus concern, and there is another side which is linking the natural resource to technical resource, which is the IPAC equation, and both are the generalized macro scale descriptions, but we are actually still not agreeing on some of these aspects. People are criticizing both of them. And so summary of arguments, design for sustainability in earth system resource flow design. So component first design is not guaranteed to converge on a desired system. What we are doing today is all products are components in a system sustainability sense. And sustainability being a system design issue, all products are only components. It is impractical to attribute sustainability at product level observations, except when allocation of resource consumption and emissions is known. Okay. So this allocation is a huge problem which we are facing. Even nations are not able to agree to the GHG emissions allocation. Okay. So this is going on. And the sustainability is not a binary variable. Okay. So it's a continuous from 0 to infinity, and tagging a product as sustainable or otherwise has to refer to the state of the environment and time. Okay. And I find, in fact, none of the product sustainability discourse refers to time, which is very surprising. Otherwise, it is non-informative. In general, product design may use relative measures to test products. So this is agreed, but information is conveyed only when you know what products and what performances are compared. So even then could be transient. So the same product in two different process contexts may cause different impacts. This is often like sidelined when projecting sustainable products in the design sense. I have like an example, like a matchstick can be disastrously unsustainable. Let's say if you throw it in a dry forest floor. Okay, but the same thing is very useful when you cook food. Okay. So that matchstick is unsustainable, this matchstick is sustainable. I don't think we can go into that level of product sustainability. So concluding remarks, relative product performance assessments using selective parameters in place. Principle is design. I think this is a key thing for my argument. Principle is solution. Principle is solution is not agreed upon in engineering design. It is a starting point. Okay, what we say reduce is principle. Okay, recycle is principle. But the principle itself is projected as solution in individual product design. And there is a need for establishing the prerequisites for taking the concept of sustainable product design beyond normative systems. And a framework of system component structure, that's what I am proposing as a logical extension, okay, despite the challenges in defining boundaries. Okay. And while products are produced and used in multiple contexts. Some of the references are used. Questions?
So, given all of this, what should product designers do in light of this impossibility to design true sustainability? How should individual designers take it?
Individual designers should know the limitations first of what they are conveying. Okay, and before making any claims about the product is sustainable, I think there should be a lot of information required to substantiate that. And whether they have the information or not is the question that has to be answered first. If not, then the caveat should be maintained. Just like we have caveats in many products which says like this should not be used in this context, okay, this is not meant for something. And we don't have such caveats mentioned in design for sustainability. And if you ask me today whether we can list out all those things, I don't think we are in a state close to that. Yes.
I'm curious how you use, how do you include emissions in your model?
Yeah. I can actually, can I go back? The same depiction, this can be used for emission as well. If we say instead of resource, this is emission. If this is emission, then the emission has to be reduced, but it won't be consumed. It will be the direction will change. The products will contribute to the emissions, and the emission has to be reduced. So this box should reduce by putting the emission coming from here, and this is the alleviating initiatives. When we have carbon capture and those kind of things will come here, and this will be the emission from this to this. So the direction changes, but you can still use the same formulation. Thank you.
So next up we have Derek Carlson.